Yeah. So I have started the recording. So I'll create a Python notebook in day 7 and I'll name it as day 7. Yes. So SQL is not a very big deal. It's very simple and it also work on indexing. So we have to fetch the data from different tables which further has some data. Okay. So before writing any first SQL query or anything, I would like to tell you some basic details of how we will be using it. So I have shared a link of cast job uh, with you. So you have to log in your account or create your account in the Sai server. And when you will come to this thing, my database, my DB, you will see there is four options: view, tables, functions, procedures. So you have to click on tables. Okay, so before that, you have to select the survey you want to for which you want to get the data. Let's say I want to get the data for DR18, which is the latest one right now. So when I will click on tables here, you see I have a lot of tables. Tables contain data sets. Okay. So when I will click on, let's say, GALS spec extra or GAL spec info, let's say. So you have to wait for some time because this website is a bit heavy. So these whole, yeah, so it loaded. So these whole data set again contains some rows and columns which have these all data. So basically, gal spec info contains the flux of the galaxies, which is used to create analysis of BPT diagram and classification of AGNs in particular. Like we have here the equivalent of O doublet and oxygen doublet, and then we have another flux values. Then we have H delta and another values, and similarly a lot of fluxes like nitrogen doublet 6584 value with error and with instrumental resolution and etc. Then we also have chi-square value for the linear fit for that specific measurement. Then we have a lot of like almost all of the useful spectrum along with this sigma Balmer, which is the velocity dispersion measured simultaneously on all Balmer line for that particular galaxy. Similarly, this is the data for the galaxies which are captured using the SDSS survey. Okay, so basically SDSS is a survey. The telescope uses the aperture point observatory. Okay, so it's a survey. So then we have this stellar mass forming. If I click one of these, you will get some information. So the one of okay, so we have this log mask in the solar masses for the best stellar mass of the galaxy, and we have the RAN deck for the galaxy similarly, and then we have the star formation rate for that particular galaxy, I guess. So, however, we have these a lot of things we can't just guess anything what it particularly specify. However, there is a definition description here what this indicates, but we have to explore the data using the FITS file by downloading the FITS file and look into it. So for that purpose, like most of the FITS file might have two or three tables, which is like journal tables, which have the spectrum or etc. something like that. But for the specific data download, we need these particular tables on based upon our research requirements. Let's say we need the galaxy spectrum which we will be using in the next lecture when we will be plotting the BPT diagram. So we will be using Astroquery plus those particular columns tables to plot the BPT diagram. Today only we will learn how to fetch the data. So we need these particular data which are not available in normal FITS file. So specifically we have this spec object all and this is very useful. Let it load. So you have to wait like for 5 to 10 seconds because this take a bit loading to come here. I just clicked on it again. Similarly, we have like another galaxy spectrum, info galaxy spectrum line, and other useful data. So here we have the galaxy spec all. So this have every information about the sigma values and all that stuff. So noise ratio we have in the different bands, and another stuff that are mostly instrumental. So this must also keep a track of what we are doing for that specific galaxy. So similarly, if I so these similarly we have these all kind of things here. So one more very useful is the photo object all. So you see here in the photo object all we have a lot many things, a lot many fluxes for different bands and all that stuff. So you can explore this also. So we have the magnitude value in the different bands with the error also. So it deals with the photometric data. So you can read this definition here. All primary and secondary objects, especially, essentially, this is the view you should use unless you want to specific object that type of object. Okay, so there is one more thing. They have different numbering for stars, galaxy, and other things. So for galaxies we have the index is equal to 3. So whenever we have to fetch the data we have to specify the index if we want particularly galaxy, otherwise it will collect all the data including the stars and the galaxy for that specific array and decoration. So this was what I want to show you. So there are now two things. Either we can use Astroquery to fetch the data, and another thing is uh, this second link. If you click on this second link, you will come up here. So it has an example, this query already written here, which says select the top 10 values, top 10 samples with the photo from the photo object as P. So similarly, we use in astronomy, computational astronomy using Python, like import as from astropy.io import fits as FIA, or we have from matplotlib import matplotlib as plt, or import numpy as p. So similarly it has written from that particular table, which must be very sensitive in the words, because if you use this o as capital or small, it will not run the query, it will throw an error. So you have to particularly copy that specific name whichever is mentioned. If the s is capital here, then in your query the s should must be capital there also, as P. And then it has also joined some more spec info table in the same value, in the same data set where it will be fetching the query. So now where it has written it has actually gave a condition that the u is basically the magnitude of that specific object must be between 0 to 19, and the g band must magnitude must be 0 to 20. And so what it is fetching, it's fetching the object id, ra and dec, and u, g, r, I, z values for that specific top 10 sample. As you see here in the photo object all, we have these values of g. Yeah, somewhere here we just looked in there. So yeah, these magnitude actually this code is fetching. Okay, so G, U, G, R, I, Z, and then there are some more values. I don't know what they are, and then it is also fetching the class and the redshift. So Z is the redshift, so it wrote it as redshift, and these are particularly basic column. You can fetch it. Most of the time we do fetch it because it has some data when the object was captured and all that stuff. Now this is the basic query, which is given by the uh, SDSS. When I will try to run it, so you have two options: either get the data in the form of its file, either get the data in your my database, which will come here in the my database, which is not right now recommended because it will be very hectic to first log in and download, and again go to download database and then download your files. So it is recommended either get first go for the HTML to look if your query has run properly. So when you will come here, you will see you have the results, so there is no error, and you see this is the whole data table. So it has the value of this magnitude bands and the RA and DEC, and specifically you have the class as galaxy star star galaxy. So top 10 sample is the mixture of star and galaxy, because in the in that particular column, or in particular SQL query, it is not written mentioned that which type of class it need to be selected. So it just wrote here that it need to know the class of that particular object, but not specifying the particular class to restrict as a condition. So then it fetch redshift as uh, redshift for the specific galaxy. Now, since we know that there was a z already written, hence it called s dot z as redshift, so that in the column it shows redshift. Now let's say I wrote R to be capital here, and again submit the query here. Now when I will come here in the same database, you see the R is capital here. So you can also change the column name by writing the first thing which need to be same as it is in the table, and then you can write it as redshift or some words for that specific column. Then plate mgd and fiber id, this will combine to form that specific link for the for fetching the further data of that specific galaxy. So whenever, like for example, you download a spectrum of a galaxy, you might see, let's say I'll just show you. So you in the link you might see some of the numbers, like spec and another numbers. If I'll just go here in our previous lecture when we, so you see, this is the code of the downloaded file. It is actually spectrum. Then there is three numbers, and these three numbers are exactly same similar to these: plate, MGD, and the fiber ID. So this is always unique number, so that even if you mess up with the RA and deck, you can get these number and find out your galaxy also afterwards. So this is a safe zone. We mostly fetch these three things also while fetching the data. So this is one database. Actually, I use SDSS a lot. Similarly, we have a KEC data set. I'll show you. So when you have to go to this link. I'll just share this link with you. Yeah, I'll share these links with you in the Slack also. And I will write this link in the Jupyter notebook as well. So I'm just giving you overview before we get started with the stuff. So most of the portals are very slow, so you have to wait for some times. Okay, so because most of the people use these column, and these are built on the very old architect of a technology. So this is the similar data I use for the polymetric data set. So most of the cake data is very useful for the polymetric analysis when we are dealing with spectropolarimetric especially. So these are the visible band, and these are the names of the instrument. And then similarly we have the near infrared instrument, which are taking the taking the observation with the range of 1 to 5 microns and 0.3 to 1 micron for the visible range. And you can even specify the date for if you want to know want to find the specific observation on that specific night. However, this is not that much used until you want to know that specific thing, so you can leave it. Another thing, you can directly write the name for that specific galaxy. For example, if you have like Seifert galaxy, this telescope is mostly used for to fetch the Seifert type 2 galaxies, because they are not like much visible in this. They don't have much visible uh, amount of range from the AGN part or the nucleus part. So this use the polymetric spectropolarimetry, which is very easy to get the information about what's happening in the nucleus for the Cypher type 2 galaxies. However, I know most of you might don't know what's a cipher type 2 galaxies, which will be explained in the next lecture when we will be explaining you the AGNs. However, you for the sake of today's knowledge, uh, just keep in mind that Seyfert Black Sea has a lot of dust around their nucleus, and which blocks the light to come in the telescope from the nucleus. Hence, spectropolymmetric help to just cut off that bad part and get the light from the center. So similarly, you can let's say I'll just write this example here, and you can set the radius. I'll just set it as it is, and when you will search it for now, I want to tell you that I have never used any query or Astroquery or SQL for fetching the data of Keck Observatory. I don't know why. I have also not found any information how to use Astroquery for Keck Observatory, because most of the data revolves around 20 cipher 2 galaxy for my part of research. So when you will run it, you will so it will take some loading because it will fetch the data for all that specific observations for that particular object. Then after that, you have to submit your email ID. So it doesn't like unlike this SDSS, which opens the data in the web server only. Keck doesn't provide the data in the web server openly. It will send you the database in your email. So you will so yeah, you see here. So it says that you can either send the results via the email, or you can bot the query. So these are two options in the Keck. So for now, we won't be using the Keck observatory for our analysis. We will be just revolving around the STSS. Okay, so I'll go back. You have just like here, you have to submit your email ID, then it will send you the data set for that specific galaxy. So yeah, so this is how SQL work. So first of all, uh, okay, so now as you got it, what and how these things work. Now we will go in the form of Astroquery to fetch these things here. So similar to these things, and then we will even specify the class, and then we will fetch the uh, flux values as well, because we will be needing it for agent plot. Just a second. So I'll come back to the day 7, and yeah, I already opened the notebook. So there are two things, there are two methods to plot to fetch the data. So now first of all, we have to import Astroquery. So Astroquery is also a part of AstroPy. So how I will write, however, it is like a different uh, package, but it is owned by AstroPy community only. Astroquery.sdss. So you can also go for MAST. MAST portal is also one of the portal, and then we have Gaia. So these all things work in the in SPS in the Astro query. So based upon your observation, you can look after how to fetch the data for that specific surveys. However, for SDSS, and other different telescope, the table name will be changed. So there is no specific template or something that will be used in all those cases. So for every dataset, the query will be different. So now import SDSS from astropy.coordinates. We will be using some coordinates to specify the range and the sky position. Let's say coordinates import sky code. So you must know that the S and the C must be capital because of inbuilt function of astropy. Then I will import the units as U. Now I will write the code. I will specify a variable for the coordinate range, and now I will specify the coordinates let's say RA will be is equals to 100 times 100 times degree, unit degree, U in degree, and similarly dec will be is equals to, let's say it start from 0 only. Okay, unit degree. So since we are using SDSS, it will be very good to like go for the 180, let's say. However, you can also find out in the 100 range also. Now we will be writing query. So this will be the query. Query, I will define some variable for the query, and now I will call Astroquery this SDSS here dot query region. So this is basically the function inside it. Inside it, you have to write query region. Then query region will be include the coordinates, and then the radius around which it has to revolve. The which was like 30 arc second in the Keck data set we just saw. If okay, so I just crossed that website. So you can also specify this radius. Let's say we have 0.05 degrees here. So unit degrees, because we are working here also with degrees. So let's say, and the spectro is true, which means the data set must have the spectrum. Now this is a small query without any SQL right now. We have not write any SQL right now. It is just inbuilt features of the Astro query. Okay, now I'll print the results here. So for this you need internet connection properly, because it will be fetching these things from internet. Okay, now query. So let's say I want to print the first five values. So I will just write here five. I have used like from 0 to 5 values till the fifth index. So this is indexing basically used. Okay, so it gave an error that perhaps you forget a comma. Okay, yeah. So yeah, of course I have to write comma after this. So yes. So you see, when I run this, there is a huge data set of all of that specific required columns. So I have not required any column yet, but there are some more columns inside it. So you see, it printed the first four random data sets. So if I go like Control C and go to the survey navigator, and I'll just write the array and deck here. I don't know if it will be a galaxy or something. So you see, it is something like a star or something. So if I go here, you will see it was a star or something, or some maybe it's a star. Yes. So yeah, you see, it's a star type. It is written here, and it has spectrum. Since we did the spectrum is equal to true, so we get this spectrum for this star here. So yeah. So you see, we don't have H alpha or something right here in the star spectrum. I don't know why it is not mentioned here. Okay, not mentioned here, might be there. Okay, in some other form. Then we have another data set. So we will write a similar query with some more complex variables, and after that we'll go step by writing complex queries. Now, uh, as we know, we can the one method first method is this, the another method is using SQL. So now we will learn how to make it using SQL. Okay, so I'll define a query SQL underscore query, which will be is equals to these triple parentheses, and now here I have to write the normal SQL language. So it will be like select, like let's say top 50, and in the top 50 it will select p dot that photo object like photometric data, which will include the array of course, and then deck of course, then let's say the value of g band, and let's say value of r band, and let's say value of z band, for example. Okay, now also let's say from spectroscopy data, from spectroscopy data, it will fetch the redshift also as red redshift table. Okay, now I'll go back in the main root. Now I will write from photo object with the particular thing, then capital ASP. Then I will join the photo. You have to make sure these particular keywords must be capital. Then spec object as s on p dot object id is equals to s dot best object id. Now what I have done here in this line, I have made sure that the tables must fetch the same values for that specific galaxy. So I have like here mentioned a condition that the object id of both of the data, either in the photo object table or either in the spec object table, it must be same. So to prevent the wrong data. Now where I will specify here a condition, let's say redshift, as let's say redshift is equal is between 0.02 and 0.1. Okay, so let's say this is a very small query we just wrote here. Now we will normally go as results is equals to sdss dot query, sorry, underscore SQL. Then I'll mention that this variable name underscore query. Now I will print the results. So it will take time because it's going and fetching the results. So it depends upon your internet connection as well as the server connection of the SQL of the SPSS. So yeah. So till then, I'll create a markdown data mining using SQL and useful useful links. I'll just write all the links here. So okay, so we have main navigator, so it will take a bit time, so till then I'll just wrote these things. So yeah, also our query is done. So we have a error here. It says so connection portal request timed out. Okay, so it is some like error from the server side, as I told you. But what we will do is we'll go to this thing here, and let's say we'll search the same query here. First of all, we have to verify if our query is correct. So we'll submit this. So yeah, it says there is an error arithmetic. So yeah, we forget to write comma after the p dot z. When I'll run this, so it's results is not defined, so I'll just correct the results. Huh. So it works so fastly. So yeah, I just missed the comma here. So you see you have the array deck g r z and redshift in the form of float. Okay, so you have these all data set for that specific uh, top 50 values. Let's say I'll just define it to top 5 for now, and it will go and try to fetch the data. And now you can also plot the variation of the redshift for those galaxies and the color magnitude diagram because we have the G and R. So let's try to plot the color magnitude diagram for the this real data. Okay, so let's say we have these five galaxies. So now let's say we fetch 500 galaxies here to make a color diagram of SDSS. However, I will not print this. So until it goes under the processing, I'll make a color magnitude diagram. So just a second. Color magnitude diagram. So I will be using the same results here. Okay. So you have to import NumPy and Matplotlib also here, and which is not plotted imported here. So I will just import matplotlib dot pyplot as plt. Also, I will import pandas because now we will be working with tables. So let's say pandas as pd, and now I will define the data frame or data set as results. This results. There is a function called toPandas which will convert the tables in the form of pandas so that we can use the pandas command. And now let's say color will be is equals to the difference between the G and R band, of course. So it will be the difference between these bands to find out the color magnitude. So yes, now we will plot. Let's say scatter for those colors and with the R band. Then let's just okay. So we can define the color is equals to purple. Okay, now let's say there is one more thing I'll tell you. We have to invert the color, invert the y-axis for the measurement. I'll tell you why. Okay, so before that I'll just try to plot. It is actually like uh for the color magnitude diagram the axis is like inverted, similar to the Russell diagram for the star magnitude. The axes are inverted to make it look uh, like something readable. Okay, so yeah. Okay, now we have this thing here. So in the Russell diagram also the axis is inverted. The diagram you see, the x-axis is inverted for those diagrams. There is a software called Topcat, so which is also used for the plotting purposes and stellar astronomy analysis. So, but it is we won't be using it for now because it's not much used in the galaxies part. Magnitude diagram, and we will finally plot it. So I have not just right now plot inverted the column here. So I will. So you see, we have a color diagram, but it doesn't look like what we need. So if you have looked on the color magnitude diagrams, okay. So now let's say I'll just go and use the GCA just like we used yesterday by doing the background black. We will not be using the black one. We will be using a function known as invert then underscore the name of the axis to invert that axis. So we will be using GCA then dot then invert underscore y-axis. So it will be something like this. And yeah, now you see we have a beautiful color diagram. If we do one more thing here to 10, so I just made these balls, scatter balls small. So we have the scatter diagram of those 500 data sets, which include both actually the galaxy for now, and as well as the stars. I don't know what is the class because we have not called the class in those values. Okay, so okay, so here you can also mention the type also here. So we will be creating a different SQL query to mention the type here. So for that, let's say we write a query again. Let's say query is equals to a new query which has, let's say, select top 100. It will actually select the random top 100 values. Okay, so it is not specified that every time you select the top 100 it will give the same top 100 values. Okay, so we will be getting some spectral data set now. Let's say we get RA and deck and redshift and error in the redshift. So I know what is the particular name, like S dot RA for RA and S dot Z capital E and RR for redshift error. So if you don't know, then you can look upon these values because you have to write the same name after this S and R. Okay. So you must keep this link with you such that you have all track for that specific data set. So, for example, it is fetching right now. It is fetching from the DR18 data set. So, based upon that, you might need the same particular data set, the table names. Let's say S is equals to deck and S dot Z and then S dot ZERR. Okay, so we have this now with us, which will fetch these four tables. Now from spec object S and uh, yeah, just a second. Okay. Yeah. Okay. So I have okay. So I'll tell you one more thing if that works. Okay. So now we have to specify where S class, the class come under the spectroscope spectro object data. So you have to keep that in mind. So galaxy and and you can also type, if we also fetch like s dot class here to verify if we have the galaxy. So now between, okay, 0.02 and 0.1, let's say. So now I will run this same query here, same thing here. So I'll result underscore, then I'll change this to query. So you see it's running here. So when I will run the results underscore, you will see we have the 100 values and class is galaxy and it's in the string 6 type data type. Now one thing more, since we have specified the class as galaxy, if we specify this as star, so you see here it will be going to give us stars. So now there is a catch here. So there is no star between this here for this specific data set. So I don't know why. Maybe if we don't specify this thing here, we might have some results. So yeah, it was due to that particular range. That specific range of the redshift was not studied in the stars. So you see, we have the stars here with this that particular redshift. So you see the minus in the redshift indicate that it is blue shifted, that the star is coming toward us. So it is very close. This star is very close to us. If I just go and look at the navigator, let's say. So so yeah, we have this bright star here. So you can see here the spectrum of this star here only. So it's quite like narrow line also. So yeah. So this is a way you can query the data set of the real time in real time for that specific data. So this is what we were supposed to do today only. So not something very long stuff. Now we will be looking at how to fetch the values of flux. So we will be writing a big query. So we have to like fetch a lot of things. So before that, there is one more thing. There is also called something type. So I'll tell you that thing also. So we can either writing like class is equal to galaxy. You can also specify the type. So we'll write one more query here. Let's say query underscore, which is equals to. So there are total six types. Okay. So before that, I'll write those six types here only. So the first type and let's say object and let's say meaning. And this is only for SDSS. Okay. So the type one. So I have to write the type like this because you have to write it in short. Okay. So yeah. So type one is equals to type one is unknown, which is not defined, like not classified, unclassified. You can say classified. Okay. Then type two is cosmic rays. Cosmic rays. Okay. So yes, as the name suggests, it's a cosmic ray hit. Then the third type is galaxies. Okay, galaxy. So yeah, extended object you can say extended objects. Yeah. So then fourth we have quasars. Okay, so photometric data for them or spectroscopy. Quasars, QSO. Okay, it's quasars. Then the fifth is sky. So it is the background, sky background. So just a second, guys. हेलो हाँ जी सर हाँ जी वो वापस नहीं करना हाँ जी हाँ जी एक मिनट सर 1530 1530 ओके okay so then we have the sixth one as star just a second it automatically turned on the background music. Okay, so it automatically turned the background music in the background. So yeah, so it is a source, point source, source. Okay, which is stars. Okay, so these are 5 classes. So I'll just a second. What happened? Okay, so I just messed up here. I just cut all of those. Okay, so just a second. I have to see what can I do. Yeah, this would be nice. If I try to make it in type. Yeah, now this is fine. If I can also, yeah, I guess. Okay, so we have HDSS type here, and you see the types are here, and you can use these numbers directly instead of these class. So basically these class are the object class along with their name. So whenever you have to fetch like write class here, you have to write this second column here accurate, accurately like this one, not these things here. So these are the particular with respect to those abbreviations used, and this 1 2 3 4 is can also be used in that data. So let's say we need the galaxy again, but we want to use a type here, okay, rather than that specific galaxy. So let's say we have to find out the galaxies. So now what I will do here, I'll write this same query. Let's say whole of this. I'll copy this here. Okay. Now instead of s dot class, I'll mention the type here. Okay. So I'll cut this. I'll write here type is equals to 3. Let's say I need stars. I need galaxies. Let's say type is equals to 3. Now when I will fetch this, you will see. Okay, so there is some error. Okay, let me just try to change the name. It says number of atoms inconsistent. Um, I have to check where is the error. Somewhere else I have used as SQL query. Okay, so it's let me check the query. Top 100 R3. Let's okay. So if this is correct, this is correct. The type is equals to 3. This is also correct. Then where is the error? Let's say I'll just write these like this only. Let's say I'll just fetch this thing only, and I'll call photo object for here from here. Photo object for the simpler query. Okay, so there was some error in the query only. So what if I don't write this thing here? Okay, I don't write this thing here. So okay, yeah. So here is a catch. The type 1 2 3 only works when you are dealing with the photometric data. Okay. So when you are dealing with the photometric data, you have to write type 1, type 2, type 3. When you are dealing with the spectrometric data, that is table, spectrometric table, you can't use this 1 2 3 type. Okay. So similarly, when I will just use the same thing here. let's say, just a second, I'll delete these things and write GRI, and here I'll just, when there is one table, you can just go for without like writing from that table as the short form of that table. So you can just specify that thing only. So yeah, we have this table here. Now this is only for those galaxies only. Okay, if I just find out, if I'll just want to verify if our query is right or wrong. So I'll go to those query here. I'll just write the RA and deck for, let's say, first one, because there seems some ambiguity. Um, so yeah, so there is some, okay, okay. So it just got the galaxy from somewhere, a very dim galaxy as per the SPSS. I don't know from which patch of the sky it just got this thing here. So more, the strip is studded, and then there is some blackness here, maybe some shift or some cutoff. And you see, it is a galaxy type. Okay, so it is like classified. However, it is very dim here. So yeah, when you will see here, there is a little like shape of that particular object. I don't know how they just classified this. Maybe some particular properties or something. So this is defined as galaxy. But they have mentioned when I hover it, like star or galaxy, but some bright stars are misclassified as galaxy also. So there is some misclassification in morphology. For that, we have built that pipeline, which run machine learning, deep learning model, that is Glamo, that we will be using tomorrow to accurately get most accurate morphology for that specific galaxy. So yeah. So this was the thing I wanted to tell you today only. So nothing much. Now we will finally write our last query for today. So this is a very short lecture, right? So now we will be writing a query for finding out the flux for that for the galaxies. Okay. So now, and also we will be using that query to so most of the times we have not we ha the right now we have just wrote a query and get these data here only in some staging area, right? But we have not fetched it as CSV or something like that stuff. So now we will be using that, fetching flux values. So now I will write a query. Let's say query underscore flux, which is equals to. So let's introduce Glamour also today. Okay, so let's introduce a bit of Glamour today, a part of Glamour today. So we will be using Glamour also. Okay, so let's say, so we have to, let's import some more functions. A bit of Glamour. Let's do it today. So Astropy, Astroquery. So we have to sorry, yeah, Astropy dot tables. So yeah, now we also have to import the SDSS. We will be using the astroquery.sdss, which we have already used here. However, for the convenience, I will just write it again here. And we will also use pandas from pandas. Oh, from import pandas. pandas as PD. Okay, so these are three things. For downloading Glamo, you must write this thing here. Uh, Sorry, I'll just make this code again. So I'll just run it. Yeah, so to download Glamo, you have to write pip install Glamo. So it will run, it will take some time. So yeah, Astroquery is so it will take some time to run. Okay, so yeah, these are some messages from Glamo that all models are running because it used deep learning models. So it shows you that some more information about since I am using the Mac version, so it can't find these things here on Mac. So it run the Metal. Metal is specifically for Mac. So TensorFlow Metal version in the background. So yeah, so it's already downloaded for me. So it Glamo mostly depend upon the TensorFlow 2.10. So that's why I recommended that you must not download a latest version of Python because TensorFlow is not updated yet. I don't know now if it is updated or not, but in like November or December it wasn't updated. So yeah, this is how you have to download the Glamo, like pip install Glamo. So I'll just delete this part. Also, there is a thing if you don't know how to download these things, you can go to this library, this website pypi.org. Let's say I'll just try to log in. So without login, also you can the things can work. Okay, so it's asking for some things. Okay. So now you can go for like search for let's say Glamo here. So you will see there is one Python package named Glamo and it says how you can install this here. So you can contribute like this or something. It will show there is a website for Glamo and all that stuff. So yeah, glamo.org. Similarly, we have for Astropy. So you will see this astronomy and astrophysics core library. So last updated was 2025. Similarly, we have it for Astropy. This is a website. Pip install Astropy. You can install it like this. So they have all the information mentioned here. Okay, so this is the Astropy library. So yeah, so this is how you can go and check. Now we'll write a big query. So we will select top 1,000 uh, galaxies. Okay, so this for now there are two things. First of all, we will be fetching the fluxes. The fluxes are all in the galaxy spectrum line. So okay, so we just saw here. If I go to the G, it's all alphabetic. So when I will click on gal spec line, so you see, as told you, here we have all the flux names. So we'll write that here. Select top 100, let's say 1,000, because when we will be plotting the BPT diagram. So BPT diagram, let me show you what is the full name of BPT diagram. Astro. Okay, so this is the BPT diagram here. So there is a small essay on BPT, essay on you can say article, a very short. It is named after these three scientists. So it helps to classify the AGNs and the star forming galaxies based upon the fluxes. Okay, so now we'll get back to our query, and I'll write we will be using two galaxy informations. So first we will be using gal spec info for fetching the normal information of the galaxies like spec object id, plate id, and mjds, redshift, and ra and dec. So ra and dec are more common, more mostly common in every table, and the object id is also very common. And then we will be using gal spec line for finding out the flux and flux width and flux errors, etc. So yeah, so I'll just write I. Let's say gal spec info is will import it as I. So I dot spec object ID comma, then I is equals to RA, then comma. Don't forget to write comma, okay? Then I dot Z plate ID comma I dot MJD comma I dot fiber ID. Then I guess it's fine. Then we can go for the, let's say the line, let's say we will define it as L dot H underscore alpha. Make sure to write this name just as I am writing, because I have these things in mind now, because they are in the running letters and separated by the underscore. So Galamo also uses the same abbreviations for these. So if you will make the column as F capital or something, the Galamo will give you an error. I'll show you how. Okay. So yeah. So this is one of the Galamo's uh, package, inside a package or function, you can say, module. We are learning today. So yeah. So tomorrow's lecture will be more the theoretical part, because we have to learn about the concepts of agents and all that stuff. So it will be less on the coding side. And then after that we have to discuss a small project we will be doing on agent analysis only. And then we'll start the project. So let's say, yeah, the flux value is right here. And 2 was 6584, I guess, underscore flux. So then we have L dot sulfur doublet, both the sulfur doublet with both of the wavelengths. S is equals to 6731 underscore flux. Then we were left oxygen singlet, oxygen 1 300, then underscore flux comma. I guess, yeah, we have this, yes. So to make a BPT diagram, we have to write a worst or a very big horrible code. Okay, so very big and horrible code for drawing the BPT diagram, because we have to write two formulas, Cooley and Kaufman formulas, that we will be learning tomorrow. We will be understanding those formulas tomorrow in the tomorrow's lecture. We use those formulas to make the lines and all that stuff, and it is horrible. So Galamos help us to package that most horrible formula into that package and help us to make the BPT diagram in one go, in just one line actually. So this is not a part of Galamo. So okay, so you will have to just write one line and import your data to plot the thing. Alpha equivalent. So let's say now we have to find out the equivalent values. So however these things are not much needed. So we'll import these values. However, L dot and doublet with 65884, these things, and then flux errors, of course. uh, I'll just import all of these, because these this will remain same, and just we have to write ERR after that. Okay, so I'll just write RR underscore RR underscore RR underscore RR underscore RR underscore RR underscore RR. Okay, so we have these fluxes here. So for writing the comments like we do in Python, we have this thing here, flux error. So this is actually a comment in SQL. flux flux. Now fluxes. Now from gal spec. Oh, spec and info I capital as I join will join the gal spec line as L, where on I spec object ID will be is equals to L dot spec object ID. Okay. Now we have to define, let's say we'll define some range of redshift where I dot Z between 0 and this. However, we can also define some more flux constraint, like let's say the flux error between greater than 0, or like flux divided by uh, uh, because BPT diagram, the back end of the BPT diagram uses the ratio of these fluxes, right? So we can even define that the H alpha by that particular thing for that particular ratio can be greater than this ratio, this value or something. However, we will not make that thing here because we are not particularly fetching some query for our real-time research right now. We were just fetching out for a BPT plot. So I'll just make this query here till here. Now what I will do is I will write here result results result flux is equals to sdss dot query result query underscore query underscore s square. Then what was the query name? Query flux. Then now if we get the result, I will write a query to fetch it as a CSV file. Okay, so if result underscore flux has some value, uh, then table, we will use the astropy table to make it a table of that particular result, and we will write that table. So these are all the function in the astropy tables. Okay, so it helps us to write it as a CSV file. Now it will write the table in, let's say, agn.csv, and format we will define here. Format is equals to CSV, and then we will allow that in future overwrite is equals to true. Okay, now print query success. Okay, now else if we didn't get any result, it will print no results returned. Okay, so yeah, so now you see it's running and the kernel here is also running. So it gave me some error here. Number of header columns 1 inconsistent with the data columns 2. So where is the error? So maybe the query is somewhere wrong. Okay, so this is the most horrible thing when you write this much big query and there is some specific small error. What I will do is, okay, so this line is good. Let's say I'll just do it something like this to make it clean. Okay, so I info is correct as I, spec is good, spec line is good as L on I spec object ID is equal to L dot spec object ID. Okay, it's good. Then we have these columns here. Okay, so I'll just try to run it once. I removed the comma from here. Actually, I applied the comma, but I don't think that must create an issue. But the way it is taking loading, maybe it is fetching the data correctly. So I just wrote the extra comma here at last. So yeah, I guess it's running the query properly now. So let's see. Let's wait for some few seconds because it has to fetch 100 values, 1000 values. So yeah. Okay, so we have to wait because 1000 is very much. Till then, if you have any question, you can ask. So okay, so it gave a error. It gave me a connection error. So it is from server side, I guess. So uh, for this time, what I will do is I can recheck my query by going to the server directly. Let's say SQL search here. I will write my query here to verify the things. Okay, so I think this must be issue with the network. So I'll just check it out. Just a second. Okay, so I'll just copy this again. So it must okay. So there was a server error actually. The query was absolutely correct. So you see there are bunch of data set and some of the values are even null for that specific type. Okay. Now also we will define some more things that the class must be the class. Okay. So yeah, there is nothing to specify here for the class because it will be only contains the galaxy information. So cal spec information. So I will rerun this query again because it ran in the SQL query properly. So maybe there was some glitch in my network or some network issue. So yeah, you see here it's a query success. So when I will go to this part and refresh it, I'll see the AGN.csv. So yeah, we have this data here, beautiful data here. Now we will try to plot the BPT diagram. Okay. So since we have the CSV, you have to write bpt dot draw, which is basically a function in the Glamour. So then you have to write AGN, your CSV file name, and simply press shift enter. And first of all, it will verify the columns, and then you see it will create three BPT plots in the different way. And yes, even if you can see that we have the ciphered galaxy and linear galaxy also in our sample, and you can see the distribution in the form of cross and all that stuff. And these are some of the Julian Kaufman line here, and this is the separation line here. So very beautiful diagrams. So plus now we will try to see what more are there in the Gelamo. Let's say what more things are there in Gelamo. Now you can also change the color maps similar to Matplotlib. Here map is equals to, you have to write map is equals to, let's say, bubble map. So okay, so it doesn't match. So what's wrong? I did here. It says arrays must not contain. Okay, so basically you see that our values, our data have some null values. So the thing is we have to use pandas to like delete those null values also. So the default function of the glamour works like such that even if there are invalid values, okay, so it automatically remove it. So you can see here that it has some runtime warning that divided by zero encountered in log 10, because it take log 10 values, and it finally found out. But these same functions, I guess, was not implied at it. So it shows the glamour code also, that it has defined these much variables in it, and also the map also. So first of all, we have to just delete the we have to drop those values. So let's do it fastly. So we have to use the dropna function. So for that, we will import the pandas CSP now. Okay, so I will firstly import pd.read csv underscore svg, oh sorry, csv, then agn.csv, then I will use score clean data frame, which will be using df.dropna function normally, and finally I will be saving this thing, that is clean under dot to csv, then cleaned underscore agn dot csv, csv with index is equals to false. We don't need those indexes. So this is actually discussed earlier in the code, in the previous lecture, how we can work with this. Now similarly, I will just call this value here. So I don't think now it will okay, so it gives the error again here, warning here actually. But let's see if we can okay, so actually we just plot the same actually, so that's why. So I have to write cleaned one here. So okay, so it doesn't save the file. Okay, okay, it's not clean, it's clean. And okay, so now there are some issues. It says, oh shit, oh shit, oh shit, I guess we did some mistake. Okay, so it says that these columns are not there. So check SDSS format of documentation at glamour.org. Missing values. So I guess we deleted the columns with the none values, I guess. But we wanted to delete. So let's see I have what I have done. Let's verify the columns. So, okay. Oh, actually, we did a very big mistake. We applied dropna function, which was actually used to. Okay, I think we did some mistake here. Hmm. Okay, it just dropped the whole row. I'll just check it again. So we applied just normally the drop function. So we actually did the correct thing here already. So I'll just need to check the main CSV file here firstly, and I'll go here and I'll see down. So it's taking some time. I'll just check here only. So yeah, we see that we have these things here, right? So okay, so we have one, two, three, four, and some of these. Okay, so let's come back to our uh, this thing, and let's say we'll define the axis to be 0 so that it only cut off the rows. Okay, exit is not defined. uh, I need to check now. Okay, what if, so maybe we are doing some a very small error here, I know. So yeah, it's dropping whole column. So I'll just check that that part again. So we'll not waste time today like our previous lecture. So I'll just check it, and we'll do in tomorrow's lecture. We have, because we have to do similar things in tomorrow's lecture as well. So we'll find out. Will be using the same data set. Okay. So we'll find out if there is some bug in the Glamo, or if there is a bug in our code. Okay. So because it's also giving some error from the glamour side that existed not defined, so which I can see here. So okay, so no worries, I'll check this tomorrow. So what I will do for now is I'll just make it markdown. I'll make it code, basically raw code, sorry. Okay, and run this, and I'll try to like map is equals to, I'll just try to make map again last time. If that worked, maybe there might some glitch. So yeah, it worked for the soft map. I'll check if it works for the bubble map. Okay, so bubble map is giving error. Maybe there must be some issues with the backend. Maybe there must be some bug in the from that Glamo side. Okay, because it must also not work for the another map. Uh, Okay, so yeah. So now there are some more functions which are like you can save the figure and in some form. So let's say I want to save this figure as PDF. So I will write save underscore figure, just like we do in the matlogic. Save figure is equals to true. I'll define it as true. So these are the function of these Glamo. Then we have to write the file name. Output underscore file name is equals to, then you have to write the file name, let's say bpt.png. Okay, then I will run this, and I will go here again. You will see that we have a bpt.png with this beautiful here, you can see. So basically the background is automatically removed so that we can get a like high quality image for our like paper. So yeah, so this is the thing I just wanted to show you. Also, I wanted to show you the things like the error if the columns are mismatched. So you can directly see that we already encountered that problem, like clean underscore. You see that the column was not present, the flux column was not present, so it gave an error that column must look like these similar names. And if you have still any query, then you can check the SPSS format or documentation at the glamour.org. So yeah, that was what we wanted to do today. So this was all about today. I will end up the recordings here, and if you have any doubt, you can ask. You may ask. So yeah.